And in the pursuit of interplanetary travel, the most unforgiving metric is not the height of the rocket or the volume of the tanks, but the engine overhead. To the layman, a rocket engine is a device that burns fuel to create thrust. To the propulsion engineer, however, it is a complex power plant that must consume a portion of its own resources just to keep its internal machinery running. This internal consumption, the energy required to drive the high-pressure pumps that feed the combustion chamber, is the hidden tax of rocketry. And most engines in the history of spaceflight have been content to pay this tax in a way that is structurally simple but thermodynamically expensive. They utilize what is known as the open cycle or gas generator cycle. To understand the waste inherent in this design, imagine a massive freighter ship attempting to cross the Atlantic. To move the ship, you need a giant primary engine. However, to get the fuel from the ship's deep hull up into that primary engine, you need a secondary, smaller portable generator sitting on the deck. This smaller generator burns a fraction of the ship's fuel to power the pumps. And in an open-cycle engine, the exhaust from this secondary generator is simply vented out of a small side pipe and discarded into the ocean. It does not contribute to the ship's wake. It does not help the vessel reach its destination. It is a necessary leak in the system. In rocketry, this manifests as the soot-stained exhaust plumes seen venting from the side of engines like the Merlin 1D or the legendary Saturn V's F-1. This is propellant that was carried all the way from the launch pad, fought against gravity, and was then unceremoniously dumped overboard after performing only a fraction of its potential work. In the thermodynamics of resource leakage in the vocabulary of computer science, an open-cycle engine suffers from a form of resource leakage. You are inputting a set amount of data mass and chemical potential, but you are intentionally allowing a percentage of that data to exit the system without being processed by the main function, the primary nozzle. And in a Merlin engine, roughly 2 to 3% of the total propellant flow is diverted to the gas generator to spin the turbopumps. This diverted propellant is burned at a lower temperature to prevent the turbine blades from melting, and then it is exhausted. While this exhaust provides a tiny amount of steering thrust in some configurations, its pressure is so low compared to the main chamber that it is essentially a rounding error in the total thrust equation. And from a hardware architecture perspective, this is a brilliant compromise. By venting the turbopump exhaust overboard, the engineer decouples the pump's exit pressure from the main combustion chamber's internal pressure. This isolation means the pumps don't have to work nearly as hard. They only need to push propellant into the chamber. They don't have to fight against the back pressure of their own exhaust. It creates a shallow system where the failure modes are localized. If the gas generator has a pressure spike, it simply vents out the side. It doesn't necessarily cause a feedback loop that destabilizes the entire engine. And however, for a mission to Mars, brilliant compromises are not enough. The physics of the Tsiolkovsky rocket equation are brutal. Every gram of wasted propellant is a gram of payload that cannot be landed on the red planet. To break through the efficiency ceiling of the Merlin, SpaceX had to move toward a zero-waste, closed-cycle architecture. In the closed cycle, a system without an exit, the transition from an open cycle to a closed cycle, or staged combustion engine, represents a shift from linear processing to recursive processing. In a closed cycle, there is no side vent. Every single molecule of propellant that enters the engine must eventually pass through the main combustion chamber and exit through the primary nozzle at maximum velocity. And in this architecture, the exhaust from the preburners, known as the generators, is not discarded. Instead, it is routed directly into the main combustion chamber. This gas is still rich with energy. It is either extremely hot, oxygen-rich gas, or methane-rich gas, and it becomes the primary working fluid for the final explosion. And frame this as a zero-leak memory management system. In a high-performance software environment, you cannot afford to let bits of data sit idle in the cache or leak out of the registers. Every bit must be utilized to maximize the flops, or floating point operations per second, of the processor. In the Raptor 3, every milligram of propellant must be utilized to maximize the ISP, or specific impulse. And the challenge, however, is that a closed-cycle engine is highly coupled. Because the turbopump exhaust flows into the main chamber, the pumps must operate at a pressure significantly higher than the chamber they are feeding. If the main chamber is at 300 bar, roughly 4,350 psi, the pumps must be screaming at 500 or 600 bar just to overcome the back pressure and force the gas inside. This creates a mechanical nightmare. The engine is essentially trying to blow itself apart from the inside out, and any fluctuation in the main chamber ripples backward through the turbines, creating a potential for catastrophic resonance. In the hierarchy of efficiency, why staged matters. To understand why the Raptor 3 uses a full-flow version of this closed cycle, we must look at the intermediate step, the oxygen-rich staged combustion cycle used by engines like the Russian RD-180. And in an oxygen-rich staged combustion engine, only one side of the propellant, usually the liquid oxygen, is run through a preburner to power the pumps. The resulting exhaust is a hot, high-pressure gas that is oxygen-rich. This gas is then shoved into the main chamber to meet the liquid fuel. This is significantly more efficient than an open cycle because the pump tax is recaptured. And however, this creates a massive thermal asymmetry. You have one side of the injector plate seeing high-pressure gas, while the other side is seeing relatively slow liquid fuel. Mixing a gas and a liquid is a slow, messy process, like trying to dissolve a sugar cube in cold water while a fire hose is spraying you. To compensate, engineers have to build massive, heavy combustion chambers to give the liquid time to atomize and burn before it leaves the nozzle. And the Raptor 3 full-flow, staged combustion cycle solves this by closing both loops. It has two pre-burners, one that turns all the oxygen into a gas, and one that turns all the methane into a gas. And by the time the propellants reach the main combustion chamber, there are no liquids left. It is a gas-to-gas interaction. In software terms, this is the difference between trying to merge two incompatible data formats, like liquid and gas, versus merging two optimized, precompiled streams, like gas and gas. The latency of combustion is reduced to nearly zero. The mixing is instantaneous, the burn is more complete, and the energy release is more concentrated. And the cost of perfection, material science at the limit if the closed cycle is so much more efficient. Why hasn't everyone been using it since the 1960s? The answer lies in the corrosive tax. And in an open-cycle engine, the gas generator exhaust is kept relatively cool to protect the turbine blades. But in a closed-cycle engine, specifically an oxygen-rich one, you are pumping hot, high-pressure, pure oxygen through metal turbines. Under these conditions, almost every known metal becomes a fuel. The engine does not just run, it tries to eat itself. The turbine blades are essentially operating inside a blast furnace where the air itself is a solvent. And the Soviet Union spent decades developing superalloys that could survive this environment, leading to the NK-33 and RD-170 engines. SpaceX had to take this even further for the Raptor 3. Because the Raptor is designed for rapid reflight, it cannot simply survive one flight. It must survive dozens without the turbine blades oxidizing or pitting. And this is where the hardware logic discussed in the previous section becomes critical. In an open-cycle engine, if a pump begins to overheat, you can sometimes just vent more exhaust. In the Raptor's closed system, there is nowhere for that heat to go except deeper into the engine. The system is a thermodynamic pressure cooker. The closed nature of the cycle means that the engine is a singular, unified entity. You cannot change a variable in the oxygen pump without affecting the pressure in the methane pump, which in turn changes the mixture ratio in the main chamber, which then changes the back pressure on both pumps. In the Mars imperative, why simple won't suffice, one might argue that the complexity of the Raptor 3 closed cycle is an unnecessary risk. After all, the Falcon 9 Merlin engine is the most reliable rocket engine in history, and it uses a wasteful open cycle. Why not simply build a giant Merlin for Starship? And the answer is found in the payload penalty. For a rocket to reach orbit, it must carry its own weight, the weight of its tanks and the weight of its fuel. Every 1% increase in engine efficiency or specific impulse does not just add 1% to the payload, it compounds. On a vehicle the size of Starship, the jump from the Merlin's open cycle efficiency, approximately 311 seconds of ISB at sea level, to the Raptor 3 closed cycle efficiency, approximately 350 plus seconds, is the difference between landing 100 tons of cargo on Mars or landing zero. And the open cycle is a local optimum. It is the best solution for a medium-lift, Earth-centric rocket. But for a multi-planetary architecture, the open cycle is a dead-end branch of the evolutionary tree. It cannot scale because the pump tax becomes too heavy as chamber pressures rise. To reach the 300-plus bar pressures required to make Starship viable, the generator in an open-cycle engine would have to be so large and waste so much fuel that the engine would eventually lose more thrust than it gained. And the closed cycle is the global optimum. It is harder to achieve, requires more advanced materials, and demands a nervous system, or ECU, that can manage the intense coupling of its components. But once mastered, it provides a level of performance that is essentially the speed limit of chemical rocketry. In summary, the engine as a finite-state machine in the Raptor 3, we see the ultimate realization of thermodynamic integrity. By eliminating the resource leakage of the open cycle, SpaceX has created a machine where every joule of chemical energy is accounted for. And the engine operates as a finite-state machine. Every gram of propellant enters the system in a liquid state, is transitioned to a gaseous state in the pre-burners to perform mechanical work, spinning the pumps, and is finally transitioned to a plasma state in the main chamber to provide thrust. There are no side effects. There are no unhandled exceptions in the form of wasted exhaust. And this closed philosophy extends beyond the plumbing. It defines the very soul of the Raptor project. It is a quest for a one-to-one relationship between mass and momentum. However, simply closing the loop is only half the battle. Once you have managed to turn all your propellants into high-pressure gases without melting your engine, you face a new challenge. How do you mix two screaming tornadoes of gas at supersonic speeds without creating a detonation? And this brings us to the unique mechanical advantage that only a full-flow system can provide, a phenomenon that turns the chaos of high-pressure combustion into a predictable, manageable flame. End section break. To understand how the Raptor number 3 tames the violent convergence of these two closed-loop streams, we must examine the specific fluid physics of its gas-to-gas injection. N4.2, the FFSC advantage, gas-to-gas mixing.